I understand you can hear me now. Is it okay?
Yes, sir.
Okay.
Yes.
Okay. So we now come to our next topic. In our earlier classes, till now, we have taken the consideration where we say that what can be the crystalline structure of various materials here. And we have talked about lattices, we have talked about lattice points. Then we said that motifs or bases can be assigned to the lattice points, which can be single atoms or multiple atoms. Then we talked about obviously about each unit cell. We have referred to the various parameters like directions, the Miller indices, the interplay, the planes, the interplanar spacing, and we have continued with the discussion, which is the backbone now of our next topics. I have seen your quiz test too. It is auto-evaluated, but I see that the marks scored are not very good as such. None of you scored 100. I mean, none of you scored 100% marks. There are some students who get 5 out of 6, but many of you have not got very good marks. Anyway, one of the reasons is that the questions are not directly available in Google search. So that's one reason why you will find that the score was less. I switch off the acceptance of your test or the Google form at around 4:28. That is 2-3 minutes after the due time, which by which almost 100 students have submitted it. 105 have submitted it. Some of you obviously were too late, so obviously nothing can be done about that. Okay, so we now talk about our next topic, where we say that we'll now talk about some defects. That is, there can be some what we call as imperfections. There can be some imperfections in crystals. If you go through your first year course on material science, or even if you have taken a +2 on solid state chemistry, you will find that I am in the last classes I have repeated whatever is listed in your curriculum already, maybe under material science 1 in first year or in +2 already, but we have tried to give it a different maybe from an application point of view. We are now referring it for that it becomes practically understandable that what is the significance of these terms. So anyway, so when I talk about imperfections here, we say that the crystals will not be perfect. So you do not have perfect crystals. And that is why we say there are imperfections. To classify them, we say you can have what we call as zero-dimensional imperfections, which are named as, maybe we can see the interstitials. Doesn't need much of an understanding. I will give you a brief idea and then move on to our next important imperfection, which we say is a line defect or called as the dislocation. I call it very important from mechanical engineering's point of view because I hope you are taking a course on strength of materials simultaneously. Is that right, Aditya Dwivedi?
Yes, sir.
Okay. So keep your mic on, please. So under strength of materials, what you may be doing is that that you have talked about the deformation behavior of materials. Is that right?
Yes, sir.
You talk about, you also call this as deformable body mechanics.
Yes.
So what you study there is macroscopic behavior.
Yes.
Means on a large scale, I take a tie rod or a tension member and then I say I elongate it so it changes the length by some length delta L, or I take a beam and I put a load onto that and then we say it deforms like this. So we may do something like the elastic Brewster formula, but the deformations that you talk about in those topics is macroscopic in nature, means large scale deformations, which do not need a microscope to be observed. That is what happens in your tensile test also. So if you have studied something about the tensile test or tension test in a UTM, what you observe is that okay, you take a sample, load it, and carry on the measurement of elongation through a machine or some other software that are helpful to us, and you can plot the stress strain diagram. But the deformation is macroscopic. Is it right? What we are
Yes, sir.
what we are referring to in our discussion right now is not at a macroscopic scale. Our discussions have been on a micro scale or even smaller than the micro scale, but I'll on just to compare our discussions with what you do in mechanics of deformable bodies, we say our discussions are on a smaller scale. And can I say that okay, the deformations that you observe on a large scale, macroscopic deformation, are they caused by the outcome of the microscopic deformations? When I say some deformation is happening, let us say the elongation of length is taking place here. So from this particular length now, if from which I started, now the elongation has taken place, and now the final length happens to be this L. Is it right? Can I say that this macroscopic deformation that is observed with naked eye, is it because of it has got some microscopic reasons also from an atomic level? Does atoms move? Okay, I'll put a very straight question. So when this thing happens, the change in length happens of this bar. The basic question, simple question I'm asking you is, do these atoms move? There may be millions of atoms in this bar, depending upon its length and diameter or square bar. So do atoms move in it once the change in length is observed? Is it? Anyone can answer me?
Maybe.
Anyone can answer me? So do atoms go somewhere? So if
Sir,
it
I
has n number
think
of, if this has got n number of atoms, before you start putting a load onto that, if I say that atoms are not lost, obviously atoms cannot be lost, then what happens? Do they move?
sir, I think the extent of the vibration about the fixed position in increases.
No, I'm talking about a deformation which is plastic in nature. You're right when you say it is. If it is elastic deformation, we can say that the interatomic spacing is increasing. But in the case of elastic deformation, when you remove the load, the atoms come back to their equilibrium spacing. You are right in that. But I am saying that this deformation is permanent. That earlier this length was L naught up to here, and now I say this delta L naught has taken place, and now the final length is L1. It is plastic. It is permanent deformation. Then, do we see there is atomistic movement? Okay, you can make a guess. Anyone can make a guess if you are listening to what I'm saying.
So I think the atoms at their own pace will get stretched.
Atoms will move or not? The question is very simple. Do they leave their position and go to some other position, or they do not move at all?
I don't think so that atoms will be moving.
Okay. Okay. We'll answer this question. I am asking this question specifically with reference to type of line defect that we find in crystals. We call as dislocation. I'll come to this question in a moment, because I will leave this question right now here and then move on to this question again. So it's an open question whether atoms move or whether atoms do not move when you deform. So another way to ask this question is, we have said, okay, I'll come to it in a moment. Let's go to the third point. We say the other type of defect which can be there is called as the surface defect. The surface defects, which is nothing but free surface. A free surface has to be there because a basic definition of lattice happens to be it's an infinite lattice, but that does not happen. Whatever component that you take, it has some finite dimension. So if I take this component here, I may be saying that there are a million of unit cells in it. But when I come to the outer surface of this component, this way there is nothing. So the concept of lattice is broken. So you always have a free surface available to you. So the free surface defect is already there. Second, the other defects can be grain boundaries. So in my last class, I said that you normally have polycrystalline materials, means polycrystalline or polygranular materials. So each crystal has its own orientation, but we have a region which connects the two grains. So there is a discontinuity, means the crystal structure is not the same one that you are observing there. So there are some imperfections at the grain boundaries. So we call them as the surface defects, and then there is a concept of thin boundary also, and if we have time, we'll go to that. Okay. So I already said that the real crystals that you see here, they are of a finite size and they always are bounded by a surface, even if they are single crystals. So this infinite lattice concept is not there, and a free surface will always be present. So a free surface defect is always there. Understanding the point defects doesn't take much of an effort, and we will not spend much time on it. You can have a vacancy where we say that one of the lattice points is vacant. So there must have been an atom of the same type here, but we say that because of something that this is absent here. So we call it as a vacancy. Because now related to this is that this vacant atom cannot go somewhere else. It cannot come out of the material. So it may be occupying something here, maybe an interstitial one. It is not at its own lattice position. It has left it and then gone to some other place. Now, some of us may take that you can have a perfect crystal, but the concept of Gibbs free energy, we will see in next slides, tells me that even naturally existing or nature doesn't want to have what we call as perfect crystals. So vacancies are necessary. So they are necessary, and then they can be explained from the principles of thermodynamics, which I said I will not do in this course because it will take too much of time, and it's not that important for our further discussion. So for our discussion, we say that there can be some vacancies, and if you want to get an idea regarding the number of vacant sites, there is a formulation available with us, which I think will come up on your slide in a moment. Okay, yes, it is there. So you can have some minimum number of or equilibrium number of vacancies which are always will be there, and you can actually calculate it, and we using this this expression as n exponent q minus qv upon kt, where n is the total number of sites, qv is the energy required for formation of one vacancy, T is the absolute temperature in kelvins, and K is the gas constant, also known as a Boltzmann's constant. This expression simply tells me that the number of vacancies will increase when I increase the temperature, because it's a minus sign here. So it tells me that the number of vacant sites will increase that when you increase the temperature. So this is one thing which we need to just remember there. And these are just values which we can take out for some materials like aluminium, nickel. The energy required to create one vacancy for aluminium is lower, 0.7 electron volts per vacancy, and for nickel is around 1.74. What I am trying to say here is that if there are, let us say, a perfect lattice available with us, and if I want to take out one of the atoms out of this here, this is what we mean by calling creating a vacancy. So to create one vacancy, obviously you will need to spend some energy to take out this atom from its place, and that is what we say is the required to create one vacancy, and it depends from material to material. So okay, so that's what the basic concept of vacancies is. And you can actually calculate the number of vacancies here. One of the examples which helps us in understanding the concept of vacancies is that if you calculate the theoretical density of any material, we have taken various exercises in which we have done that. If I do it for, let us say, iron, the theoretical density, assuming that all the lattice points are occupied, comes out to be slightly higher than what is practically observed. That is what you observe in the case of your experimentation. So that always tells me that what you found theoretically, assuming that the atoms are there at their position, that's not correct. There are few sites which are vacant, and that is why the actual density may be lower than what you find in the case of an experiment. So you can actually try to find out the equilibrium concentration of vacancies using Gibbs free energy, where we say Gibbs free energy G is nothing but dependent upon H, which is the enthalpy, C is the temperature, and S happens to be your entropy. So we will not go into the details of this, but just to get some idea that vacant sites are there. Now coming to our main discussion that I will try to go today for is the concept of dislocation. That is, please switch off your microphone. Akshay Chauhan. Akshay Chauhan,
Yes, sir.
please switch off your microphone. Okay, so we say there are bound to be some imperfections, and one of the types of imperfection can be considered as a line defect. I have already said that most of the things in material science are empirical in nature. That means they were conceptualized first based upon certain observations, and then they were found true later on, maybe after many years, after some experimentation techniques. So, the basic concept which tells me that there can be some imperfections comes from this first observation. So, the first observation is that theoretically predicted strengths of crystals are very high than what you actually measure in an experiment. So this tells me that theoretically crystals shall be very strong, but actually they are not very strong. There are large differences in their values, and this is what we then people thought that this discrepancy can be related to presence of defects. So this discrepancy can be related to the presence of defects and specifically to edge dislocation, to this line defects, and one of them happens to be dislocations in this context. So now I come to my topic which I was referring to in my first slide, that I was asking you that when you have plastic deformation happening on a macroscopic scale, on a large scale, does atoms move or does atoms do not move? So it is observed, and it is true also, that there is a net movement of large number of atoms in the presence of applied stress. So atoms do move. Atoms do move. But this raises another question. Once I say atoms move under the action of the applied stress, then this asks me, how do they move? How do they move? Why I'm asking it? Because we said that a material may be, let us say, having a simple cubic lattice. So if it is having a simple cubic crystal structure, or let us say a body-centered crystal structure, let us say it is there. So it is a body-centered crystal structure. Let us say BCC. And there are a number of atoms. There are a number of unit cells, millions of unit cells available. So once I apply force, then I say that atoms do move. So this asks one question, this raises one question: does this movement distort the crystal lattice? It's a very basic question. That I took, let us say, iron, Fe, at room temperature. It has a BCC structure. I put it in a machine like a UTM and I deform it. And at the end of, let us say, it has changed its length to something, or it may have bent, whatever load I apply, some deformation has happened. The basic question we are asking is that does this macroscopic deformation, which is plastic in nature, plastic deformation, permanent, does this cause a distortion in the crystal lattice also? Yes, any takes on this? Is it a question to be asked or no?
Yes, sir.
Rajil Sharma, yes. Is it a valid question? Once I say that once you take an iron bar and elongate it, we say atoms are moving in it. There is atomic movement, then at a very large scale atoms are moving in it. So then the second question obviously comes up that if the atoms are moving, it may happen that then this crystal structure may not be BCC. It may be after deformation, it may be becoming random, maybe non-crystalline, or it may go into something else. Is it a question or no?
Yes, sir.
It
Okay.
depends.
So what is your answer on this? What is your take on this? Does crystal structure change after during macroscopic deformation, or it does not change?
Sir, it
Sir, I
should.
think
Huh?
Sir, it should be change.
Then I am asking you a question. Somebody can say it can change, or somebody can say it will not change. There are only two answers. Is it right? There are only two answers that this, because of this macroscopic deformation, the crystal structure can change or it cannot change. Okay? It is experimentally observed. Now I come to again empirical observations. It is experimentally observed. It was observed that there is no change in the crystal structure. There is no change in the crystal structure. It can be observed, it can be found experimentally. And if you would have been here, we could have done it. But anyway, you are not here. That's why it's not possible for us to do that. But I'll try to give you a link where you can see that. It was observed that due to macroscopic plastic deformation, atoms move in a large scale. The elongation also takes place, which may be permanent, or bending may take place, which is permanent. But it was also observed that there is no change in the crystal structure. Iron, if it is BCC at room temperature, after deformation also it remains BCC. It does not go to FCC or simple cubic or something else. It remains BCC. One of the ways which we can do it is through an XRD analysis, which helps me in finding out the crystal structure of the materials. So it was experimentally observed by scientists that after deformation, there is no change in the crystal structure. Means the crystal structure does not deform. So it was, if it was a lattice like this, if you observe it in 2 dimensions, I say if it is like this, it does not go like this. It does not become an oblique lattice, or it does not become if it was orthogonal, it remained orthogonal. So,
Sir, I have a doubt.
yes.
Yes, sir. Like, sir, I get that how it will remain the same type of
No,
unit
it
cell,
is an
but
observation. We have not answered that why
yes,
it will remain the same. I am
sir.
saying
But
that
will there
yes,
be a change in the length of, or like
yes,
basically
yes.
the
I am
length
coming to
HP?
that. I am coming to your question. We have not answered the question. I have just raised a question that there are two possibilities. That once there is a macroscopic deformation, the crystal structure can deform or crystal structure cannot deform. Is it okay? Keep your mic on.
Okay,
This
sir.
is the question. Okay. And it was answered through experiments, not by me, not by you, long ago, maybe 100 years ago. Once we came out with the techniques through this crystal structure can be evaluated, that there was no deformation. The crystal structure does not change, it remains same. Okay. Is that right? Now comes your question that if crystal structure remains the same, then how does this deformation takes place? Means now you can hypothesize, and people hypothesized that this deformation can take place in some manner so that it does not deform the crystal structure. The crystal structure still remains the same, but the movement of atoms continues. That deformation can take place because of movement of atoms at macroscopic level. Now ask the question.
So I was asking that if we say that it is still a BCC, and
Yes.
obviously the angles have not changed, so it's not altogether a different system. But is there a change in the length parameter, that is the distance between two lattice points? Because obviously there's a net increase in the length.
No, it does not change.
Okay.
We will answer this. We will answer this in our next. This is the basic concept of dislocation. Why I have put this thing here, this discussion about no change in the crystal structure, is just to tell you the importance of dislocations, because then we will be able to understand that how does this movement takes place. How does this movement takes place? Atoms move because of forces which you apply on them, but they move in such a way so that the crystal structure is not distorted. The crystal structure is the same. There can be some distortion in the edge length that you are saying, but that too is not normally observed. So we will see that what can be the hypothesis through which people thought that this deformation is possible, and that is basically the concept of dislocations. And with this dislocation, we will try to define this or describe this plastic deformation through a concept known as movement of dislocations. So when I talk about dislocation, movement of dislocation is always very important to us. So we will try to define this concept of no change in the crystal structure, no distortion in the crystal structure through plastic deformation by the movement of dislocation. So before that, we need to understand what is a dislocation. Okay, let's come to that. Let's come to that. So before coming to that, let us talk about this very basic concept. I have shown here two planes. I have shown here two planes. And if you look at the configuration of these two planes, we are saying this is a hard sphere model of the atom. So these are all atoms which are located inside your material. Can anyone, Arshia Sehgal? Arshia Sehgal.
Yes, sir.
Okay. So we are saying that just look at this diagram, which is it visible to you?
Yes, sir.
Okay. So we are saying there are two set of planes here. They are parallel to each other. Can you see that?
Yes, sir.
If they
Yes,
are
sir.
parallel to each other, what about their Miller indices? If these two planes are parallel to each other, what about their Miller indices? Will they be same or different?
They will be same.
They will be same. Obviously, they will be same. Anyway, so I am not saying which is this plane, but anyway, if they are two set of planes which are parallel to each other, they will be the same plane. They will be having the same Miller indices. Okay. And what is this A? I can say this A is interatomic spacing. Sorry, not interplanar spacing, not interatomic.
Yes, sir.
This A is nothing but the interplanar spacing. Is that right?
Yes, sir.
And what is B? B happens to be the interatomic spacing.
Yes,
This is
sir.
basic definition. The distance between the two, the equilibrium distance between the two atoms is the interatomic spacing, and A happens to be the interplanar spacing. Okay. Looking at this configuration, it looks like a closed pack configuration. Is it? They
Yes,
looks
sir.
like a set of planes which are in closed pack configuration. Means if I go back to our discussion on Miller indices and FCC or BCC ones, can I say that if this is for FCC, this can be one set of 111 planes? If they are closed pack, let us assume that they are closed pack planes. Is that right?
Yes, sir.
111 planes are the closed pack planes. That is correct. You know that. We have done it already. Is it right?
Yes, sir. Yes, sir.
Okay. Let's come to someone else. Amikul Basut.
Yes, sir.
So does it make a sense what I'm just saying?
Yes, sir.
A is the interplanar spacing between 111 planes, or maybe anyone, but right now I'm saying that they may be 111 planes. A is the interatomic spacing and B is the interplanar spacing, and B happens to be the interatomic spacing. Is it right?
Yes, sir.
Okay. Now assume that I start applying a shear stress. Shear stress, you have already understood the concept in strength of materials. When we say
Yes, sir.
that this is shearing. So you are trying to shear this one plane of atoms with respect to the second plane of atoms. And once I do that, it may happen that after shearing, this may be your final configuration. So I'd say this is the starting point, this is the final point. Is that right?
Yes, sir.
So what has happened? We can assume that what has happened is that entire set of, so because these atoms were having bonds to each other, so they were all bonded to each other. So if I say that they will be moving with respect to each other, it will cause for breaking of these bonds.
Yes, sir.
It will cause for breaking of these bonds, and
Yes,
then
sir.
all the bonds will be broken, whatever bonds are there along the length, they all will be sheared off. And then it may come to, let's say, the next equilibrium spacing, next equilibrium position. So from this point, if I say 1, now 1 has come here, and this is 2. Now the 2 has come here. So it has come to, let's say, so it has shifted one one distance, one atomic distance. Is that right?
Yes,
But
sir.
it is possible only if all the bonds were broken along the planes. So these planes, we are saying that theoretically, just we are saying there are only 5 or 6 atoms, but there may be millions of atoms which are actually stacked like this. And if they actually shear in this way, it will need some amount of force or shear stress or force to break these bonds. It can be taken as a concept.
Yes, sir.
Okay. And this is the basic idea now. This is the basic idea now, that the atoms move when you apply a force onto them, let's say shear stress onto them, and then they move from one place to the second one. From here they come to this one. Now how do they move? One possibility of this movement is that all the bonds along the length, maybe millions of bonds, are broken, and to break all those bonds, very large amount of force will be required. And people try to calculate that. Okay, let's say to cause all the bonds to break at one instance, some amount of force is required. You can calculate that theoretically on any scale. Okay, but practical data tells that the actual shear force or the actual shear stress which will be required to cause this deformation is very small. So the actual shear stress required is very small as compared to the theoretical one, theoretically calculated one. So somebody said theoretically you can calculate all the atoms, each bond will have some energy required to break it, and if all of them, millions of them, are broken in one go, some amount of energy force and some amount of stress will be required. But actually it was observed that this actual shear stress required to cause this deformation is very, very less. How less or how much less? Let's come to this, and then we will answer that why it can happen. So I will show you this later on. I will explain it later on, and then I will explain what is the meaning of this. How much less? I will just skip through this calculation. You can go through it. I will share the data with you. So theoretically, it was calculated that shear stress tau, maximum shear stress required to cause shearing of a material, can be assumed as, it can be theoretically found that it is somewhere around g upon 2 pi, where g is the theoretical shear, g is the shear modulus. You have Young's modulus E and the shear modulus G. Anyone can tell me the relation between E and G? E, G, nu.
2g1 plus mu. E is
Yeah.
equal to.
Yes, G equal to E upon 2 into 1 plus nu. This is what is the relation happens to be. That is, G will be lesser than the what we call as the Young's modulus. Is it right?
Yes, sir.
Young's modulus values are in gigapascals. So E values are in gigapascals. For steel, it is around 210 GPa. For aluminium, it is around 70 to 75 GPa. So they are in gigapascals. So if I take this 210 GPa and even divide it by 2 times 1 plus nu, the G value or the shear modulus will be again in gigapascals. Is that right? Is that right?
Correct.
And going by that, if shear modulus is in gigapascals, and I say that theoretically it can be found that this shear stress required to cause this shearing can be found as G upon 2 pi or 0.16 times G. The shear stress must also be in gigapascals, even in single crystals. I am only talking about single crystals for the time being. It shall be somewhere in gigapascals. So we say that the shear modulus for metals is somewhere range is 20 to 150 GPa, and the theoretical shear stress then based upon this formulation must be somewhere near 3 to 30 GPa. But the actual that you observe for single crystals happens to be 0.5 to 10 megapascals. This is for single crystals. So it is even 100 times lesser than your experimental values. And this is what prompted people to think about that the crystal is not perfect. The crystal is not perfect. There are imperfections in that, and one of the imperfections can be dislocations, which they weaken the crystal. But I caution you here that right now we are saying that in single crystals, dislocations are weakening the crystal because they are imperfections. But later on, we will see that you can use these dislocations to strengthen the material also. Means I can try to use it for some other purpose also. But right now for single crystals, we are saying that dislocations can be the reason why this large difference in the experimental and theoretical shear stress is observed here. This is just the values that you find here, that for single crystal materials, aluminium, copper, iron, the theoretical values are here, and these are what you observe. So they are much less than that. And this takes me to this understanding. Okay, with this understanding, let us come to this hypothesis. So what you observe here, Ankita Soni. Ankita Soni. Lakshay Goyal.
Yes, sir.
So, can you take this figure as a two-dimensional lattice?
Yes, sir.
We are saying that it is visible to us from one side, and this is how it looks like.
Yes.
Okay. So when we were referring to the shearing between these two, so we say you start applying a shear force here and a shear force here. And then we said that our model was saying that, okay, it can happen that these atoms which were there, one plane, the second one was here. So all the atoms can slide at one time. So all the atoms can break at one time, bonds can break at one time, and then they can be shifted to the next position available for them, next equilibrium position available for them. But that there was a lacuna in that model that it predicted very high values of shear stress, which actually is not there. So then the concept of dislocation was put into feature. I will define it later, but let's try to see what is happening here. So just a minute. I will run it. Can you tell me what is happening? Lakshay Goyal.
Yes, sir.
Can you observe what is happening?
Yes, sir. The atoms are being dislocated.
But the bonds are broken one by one. Not all the bonds are breaking all simultaneously. I'll run it again. So it breaks one by one. So one bond breaks, then it comes to the next one. So only one of the bond is broken out of these 10 or 12 bonds which are visible to us. Can I see that? Can you see that? And there may be millions of them which are doing it this way. That one of them is broken here, and then
Yes.
what is happening, that there is something which you need to observe here. Let us see what you see there. That there was this atom plane which was there, which was half, and then at the end of this movement, that half plane has come here. Is it right?
Yes, sir.
So this half, I can say that this half plane has moved in such a way so that it was here in the beginning of when it was undeformed, but now once you start applying shear force onto that, the atomic bonds are broken one by one, and at the end of it, this is what has happened here to it. And we will say, conceptualize this understanding here as the movement of dislocations. And let's now come to what is a dislocation. We will make it. I'll run this simulation again once we understand what is dislocation actually. So let's come to this. So the first type of dislocation happens to be the edge dislocation, and I will talk about the edge dislocation first, and then we'll go to the other types. Okay. Shehbaz Ali. Shehbaz Ali.
Yes, sir.
Okay. Does it look like a perfect lattice without any vacancies and without any imperfections?
Yes, sir.
So this can be taken as a 2D lattice, which is visible to us, and I can say it is a perfect lattice. There is no imperfection in it. Okay.
Yes, sir.
There can be vacancies there. Some of atoms can be removed. Some interstitials can be there. And let us say what I do now is that I remove a set of atoms from here. I remove a set of atoms. An array of atoms is removed from here, which creates this space here. Which creates this space here. Is it an imperfection now?
Yes, sir.
It gives rise to an imperfection. So this imperfection we will try to conceptualize as what we refer to as edge dislocation. Not this imperfection as such, but because of this imperfection, something called as edge dislocation can be there. So this, when I say this atom planes or half of this, if I refer to this one plane and I have removed half of the plane here, or I can say this is one set of planes which has become extra. This is extra half plane. And this is the removed half plane. Is it right? Can I say it like this?
Yes, sir.
Okay. So I have put an extra. Now I take it other way. That I can say that half of it have been removed from the bottom, or let's say it has been inserted at the top. So what happens to the interatomic spacing here at the bottom? So if it was A here, now it has become almost 2A.
Yes, sir. It will
It cannot
increase.
be sustained. It cannot be sustained. And then what will happen here is this. What will happen here is this. Now, can you see that the red dots are representing a plane, which I can say now is an extra half plane. And the lattice is in 3 dimensions. So I can say that it continues like this in 3 dimensions. We are only able to plot it in 2D here, and that is why it is like this. Otherwise, the same thing is repeating. So these are all repetitions in the 3. What we observe here, we have put an extra half plane here. extra half plane here, but this is not exactly the dislocation or the defect here. Why? Because of this extra half plane, what you observe? If I observe here at the bottom, is it a perfect lattice? Let it come,
No,
it is
sir.
not there. Now, here. In this box, at the bottom. Is there an extra plane here or no extra plane here?
No extra plane, sir.
No extra plane. If I look at this portion at the top, let it come. It's slightly slow. Take some time. Yes. At the top box now, is it perfect or there is an extra plane there? This one at the top. This also seems to be a perfect lattice. Is it right?
Yes, sir. Same
The,
intra.
yes,
atomic
the
distance.
imperfection seems to be somewhere here in this region. The imperfection seems to be somewhere here in this region that I have underlined. After that, here it slowly goes to the perfect lattice. Or some region there are stains, but after that, away from it, it is all same. There is no distortion. Is it right?
Yes, sir.
So then what is the dislocation here? What is the imperfection that we are referring to? So we are referring to the imperfection here. Let's see it here. So the edge dislocation, if I try to see, I already said that it can be a perfect crystal here at the top. Similarly, it can be the perfect crystal here at the bottom. And now the edge dislocation is here along this plane. So there is a line here, this line, along this line, and this line is creating an edge dislocation. This line is creating an edge dislocation. We already said that the regions far away from the dislocation line are perfect, and the deformation is concentrated around the deformation line, dislocation line. This deformation is concentrated. There are strains in the lattice. If you look at it carefully, you can see here that here the interatomic spacing has reduced, and here the interatomic spacing has slightly increased. So there are lattice strains available here. Or in terms of simple understanding of stresses, there can be tensile stresses or compressive stresses above and below this dislocation. So this edge dislocation here happens to be now given by the plane that we are referring to here, and this is referred to as the edge dislocation line. And obviously it will continue along the depth of this. So it is only one plane which is visible to you. The second plane can be here, third plane can be here, and it can continue to several atomic lengths, several lengths here along this. So this is what we refer to as the edge dislocation line that we are referring to. Okay, so there's another way to understand the same concept here. The other concept, other way to understand this concept that people have conceptualized is that in addition to in place of talking about an extra half plane, let us say this is a perfect lattice, and what we do, we have broken some of the atomic bonds here along this plane. So I've broken some of the bonds here along this plane, and then I applied a force here to push these atoms or planes above this atoms above this plane to this side. So what will happen because of this? The planes will start moving here. So below that it is not moving. Above that they are moving, and this is an intermediate position. And if I continue this, it may happen that this initial one has come here now. It has moved one atomic distance. I will write it as B right now. And then it has come to 1. So this is 2, this is 3. And this has created now, because after that the bonds were perfect, so this has created what we refer to as an extra half plane. So this seems like an extra plane which is available to us just because you have not broken the bonds after some length. Because if you see that carefully, after this the bonds are perfect. The atoms are they are not broken. So it is this concept which takes me now to the another way to understand dislocation. So we say we now introduce one more concept of what we call as slip. Very simple to understand. The name tells me that is slipping of maybe two crystals or the same crystal or atomic planes with respect to each other. So you can say here that this part of the upper part of the crystal here, this part is slipping with respect to the lower part. So there is a slip observed here, and that is why we name it as slip. And this slip is same what we try to visualize here. Is the same slip. Here we said that these two planes can slide with respect to each other, and this is what is the same slip that you observe there. So these two planes can slip with respect to each other, and we now say that this slip can be conceptualized in this way of what we refer to as an edge dislocation. So you can now say that this has created an extra plane here, which was not there earlier, but now it is here. And this is what is creating a strain here in the lattice. So you can now define edge dislocation as a line. Now another way to define it is a boundary between the slip and the no slip region of a crystal. So this part of the crystal forward here, there is no slip because there is no the bonds are not broken. This one is slipping, so we say this is the slip region. And the boundary between these two happens to be the what we refer to as the edge dislocation line. We call it as a line defect. Keep it in mind, we said it is a line defect because this is along this line here what is happening here. And that is why we say it is a line defect. If I am saying that plane was a defect, it could have been termed as a planar defect. It is not, because we already said that the plane is not a problem. The problem is this line and the zone around this line here, which is what we call as an imperfection in the crystal. So this is what we define here as the edge dislocation line. So the same way you can say that it's a slip part of the crystal, and then this is the unslipped part of the crystal, which helps us to understand the concept of dislocation. So to characterize this dislocation, there are two vectors which we'll be using. The first one is referred to as the tangent vector, and second one, the important one, happens to be the Burgess vector. We will come to Burgess vector in detail in our maybe next class, but right now there are two vectors. The tangent vector, which is tangent to the direction. So this was your edge dislocation line. So, and this was your extra half plane which we were saying was there. And the tangent vector is tangent to the edge dislocation. So this is your t cap. And the Burgess vector here is in this particular case of edge dislocation, which we say is the edge dislocation here, is perpendicular to your edge dislocation line. So I can take that back again. So we are now saying here that this was the line here. So the vector along this is this tangent vector, and vector along this happens to be your Burgess vector. If it has moved one internomic distance, means now I can say that this is what we refer to as in our earlier concept as the interatomic spacing, not interplanar spacing. This is not interplanar spacing, this is interatomic spacing. So I'll define it once again, that in this figure, if you see, this happens to be your interatomic spacing, and in this concept, this happens to be your interplanar spacing. So we are referring to the concept of planes here. This is interplanar, this is interatomic. Or I can say that you are referring to a direction along this plane. So, and we will describe it further. So I'll this is the concept, as I said, of your edge dislocation. And I will leave it here. You have a next class, so we'll see you tomorrow.